Okay, so welcome back. So we were looking at equivalent circuit for transformers, and as I said before, the basic philosophy is the transformer is perfect, plus some imperfections around them. And where we were at was essentially this. Is this one? So these are the transformer terminals, this one and that one. They are real physical terminals, whereas everything in there, they form the model. And of course, you can't physically get in there. So you can't touch that physically. So this is only a mathematical representation. So as we said before, we have a perfection, if you like. So that's perfect. Excuse me, say it. Could you check whether the red comes up? Is that possible? No, the red color. Does it come up there?
It doesn't show, but I think it's possible to.
Yeah. Okay. We hope so. So, okay, perfect. And the actual transformer is in this box here. So that's practical. So you can see that practical equals perfect, plus all of those things are imperfections. So that's the first step in the development of the theory of the transformer. It's using this idea that practical is equal to perfect plus imperfections. We did give names to those things, and we would now put the names on. So this was R1, primary side winding resistance, R2, secondary side winding resistance. Here we can put L1 or X1. Watch my other video that I'll put on later on, so you would be able to relate X1 to L1, but it's very simple, of course. You would have to remember that X1 equal to omega L1, where L1 is the leakage reactance, which is associated with leakage flux. Similar on the other side. So that's a secondary side leakage flux, and from memory, we did talk about this last time. Now, as I say, the picture in your mind should be where is this flux? If I give you a transformer, I put it in front of you, and I say, where is the leakage flux? You have to be able to point to the path of that leakage flux. If you cannot, well, might as well go home, right, and watch TV. Okay, so, I mean, I am serious about this. If you are a power engineer, you have to be able to, if I put the physical transformer in front of you, I say, show me where this is in the transformer, and you have to be able to show me where the leakage flux is. Just like if I say, where is this? You're able to do that. You're saying to me, oh, look, yes, I can see the path, the electrical path, where that resistance is. Similarly, you have to be able to show me where the magnetic path is for that inductance. If you cannot do that, go back to first year. I hope I'm not offending you, but I am trying to get you to understand that these things have got a physical explanation for them, or a physical representation that you have to be able to see and relate and look at. So this is a path for a flux. path for flux lines. This is also a path for flux lines. So you have to be able to show me the path. It's not just a number. Of course, it is also a number that we'll talk about very soon, but you have to know what it is physically as well. And it is a path. Path for flux lines. Path for flux lines. Path for flux lines. All these are real things. Anyway, resistance, and this one here, of course, losses in the core, and this is magnetizing reactance, which again is omega times Lm, which is the magnetizing inductance. If you want to know about inductance in detail, watch the other videos that I will put on the study desk. Okay, so let's keep going. Important step that we do next, very important one, is what we call referring all the variables to one side of the transformer. And that concept is quite simple in mathematical terms, but quite profound in the concept. So you should think about it and understand what you're doing. This here is a perfect transformer, and you will give that transformer a turns ratio, which is the nominal turns ratio of the transformer. So I tend to like transformer nameplates. Every opportunity I have, I take a picture of it and take it home. About a month ago, I was in a 275 kV to 132 kV substation. And that's what I did. I took some photos of the transformer there. Plenty of information on the nameplate. And one piece of information is definitely the voltage ratio, of course. And from the voltage ratio, nominal voltage ratio, you can work out the nominal turns ratio. So that's something you get off the nameplate of a transformer if the transformer already exists. Or if you're building the transformer, then that's something that you would decide yourself. Okay, so what is done in practice? This is simplified. Hope I have enough board space here. This is simplified, and it's simplified. I shouldn't really use the word simplified. I am using the word simplified a little bit loosely here. It's simplified on a diagram, but you're not really making any further approximation. So it is still an exact situation when you do that, which I'll show you what we do soon. You're not making approximation. You're still keeping all your calculations exact. So what do? We say we refer this to the other side. And when you do that, or vice versa, but for simplicity, we'll go to the primary. So if we refer everything to primary, and I'll talk about this in some detail, so I'll put that here, referring secondary quantities to primary. So if you do that, you will get a simpler diagram, looking simpler, as I said before. So this is R1, X1, R0, X0, and I have to go small here, unfortunately. So now referring means go back there. I'm going 2 steps here. Go back there, and we put a prime there for referring, and then a prime there for referring, and we put the transformer there. We are basically converting this transformer to a one-to-one transformer. So we're basically doing that. It becomes effectively a one-to-one transformer. I've jumped a couple of steps here, but that is okay. I will explain those steps. I'll explain it here. I'll explain it in all the details that you will need. So this is a transformer, perfect transformer, just like this one. And if I put an impedance here, I could put any impedance, so I'll call it Z. I'll call it Z. So think about this. And let us say that I'll put some numbers in. So I'll have I have 100 volt here. Let's say it was a 2-to-1 transformer. I have applied 100 volts. 100 volts, and it's 2-to-1, as I say. And let's say Z here was 10 ohm. Okay, so you do a little exercise to understand what we are doing. So if that was the case, then what would this voltage be? This is an ideal transformer. So what would this voltage be? 50. So it's obvious it's going to be 50. So that's 50 volts. And what would this current be? 5. Yes, that's good. So it would be 5 amps. Okay, that's perfect. So what is this current on that side? What's this current? This one here on the primary side. So we knew 2-to-1, 100. So this is 50. 50 divided by that. Yeah. So how much is this current?
10 amp.
Yeah. We got two answers there. 10 and 2.5. Of course, 10. I'm sorry, that is not right. But thanks for the answer anyway. I think it's good to see that you're trying. Obviously, it's not 10, because if it was, then this transformer will not be perfect, because you would be putting in 1,000 volt amp, and you're getting only 250. So it's not right. Okay. So it is definitely 2.5, and it has to be if we are to satisfy the equations for a transformer. In other words, V1 on V2 equals N1 on N2, and I1 N1 equals I2 N2. If you look at those two equations, then it has to be 2.5. In other words, if you are stepping down voltage, you're stepping up current. Voltage has stepped down by factor 2. Current has to step up by factor 2. So that's the situation. So this is what it is there. Now, I don't want you to do calculations or anything like that. I want you to think. Think about this. If you had this transformer and I was to take this away, right? I was to take it away very quickly, and I were to replace it by this. Instead of 2-to-1, so this is 2-to-1 there, I make it 2-to-2. That is, I make it same number of turns here and there, which will, of course, make this 50. We'll make this 100 volts. And it will make this, of course, because it's 1-to-1 now, 2 turns to 2 turns. So it will make this 2.5 as well. And I appropriately change the impedance. and you look from this side, from the same primary, would you know any difference? Would you feel any difference if I change everything here, take it out, make it 2 to 2, which is the same as 1 to 1, and I change the impedance so that this is the same current as that side. Of course, it has to be the same because the turns ratio is 1 to 1. You wouldn't know any difference. So for the primary side, it doesn't care really what's on there. It can be a multiple. It can be a multiple of possibilities here without changing anything there. And one of those possibilities, the one that we are interested in, is when the number of turns are the same. That's the one that is best for us. And I will tell you why soon. But before I tell you why, in order for me to be able to allow the primary side not to feel anything while I do this change, that is, I'm changing the secondary from being 1 turn to 2 turns, so that the ratio is 1 to 1. If I do that, what impedance should I put here? Yeah, how much? 40. Yeah, it has to be 40 because 100 divided by 2.5 is 40. So it's 40. So again, in summary, if you had a transformer that was 2 to 1, 1 being on the secondary side, and you came and quickly swap the secondary side such that 2 to 1 becomes 2 to 2, and you wanted the primary not to feel anything, then you would have, in doing that, you would have to change the impedance to 40 ohms in this example. So to the primary side, it doesn't matter what the secondary side is. Again, a small diagram, but you know what I mean. So there are multiple secondaries that you can choose from so that the primary side wouldn't care about it. You can choose many secondary sides, from many possibilities. It doesn't care. So to it, they are equivalent. You can think of other equivalents. You can think of, instead of making it 2 to 2, I could make it 2 to 4. I make it 2 to 4. Primary side doesn't feel anything. For that to happen, if it was 2 to 4, that would become 200 volts, and this will become 1.25 amps, and this will become whatever it is that you can calculate. So you can see the primary side doesn't care what you put on the secondary side. You can change it without it knowing anything. But there's one of those choices that is of advantage to us. And the one that is of advantage to us is the one where the turns ratios are the same. That is 1 to 1 or 2 to 2 or 25 to 25. We don't care. As long as it's 1 to 1, it is of advantage to us. As I say, I did jump one step there. I will go back so that you can see the magic of this. I'll go back a step. That's a good thing about recording this. So I'll go back a step so it looks like the one on the other side. So I say I'll change this. I'll put an impedance there so that it relates to what I said before. So put a load there. So you would have here you would have R2 prime X2 prime and a load that it's there Z, but over here it will be Z prime. So I've converted the transformer from N1 to N2 to 1 to 1. And as I say, the primary side will not feel anything because I've just swapped the secondary. I've taken that secondary out and I've put a new secondary in a way that the primary doesn't feel anything. And we've given an example here where we do that. Now, why we make it one-to-one without changing anything that's happening there, you will see very, very soon why that is great. I don't think many books tell you why, but I will tell you why. Okay. So let's continue. So we know how to swap from here to here without making any approximation whatsoever. The primary sees the same thing, just like you see there. Okay. Those numbers, though, are different now. And there's a general formula for those numbers, just like you went from here to there, from 2 to 1 to 1 to 1. When you went from 2 to 1 to 1 to 1, the impedance, instead of being 10, became 40. So what's the general formula? What do we multiply by?
It's the volts over ampere.
Yeah, you're right. It's volts over ampere, but I wasn't looking for that. I said, what factor do you multiply by to get from the top one, which is 10, to the bottom one, which is 40? The square of the turns ratio, right? Okay, you multiply by the square of the turns ratio, which means that here, Z prime, it's equal to Z times the turns ratio squared. I mean, sometimes we say we divide. Let me just call the turns ratio N, where N is, I'll say N1 or N2. That's the turns ratio. And you have to multiply by the right number there, and we'll do that. Here the turns ratio is 2, and you can see we've gone by a factor of 4. That's because it's 2 to 1. What's really happening, sometimes we forget, what do we multiply or do we divide? I will just give you a trick. This is the trick. You say, oh, I am, in this case here, I am stepping down the voltage because I'm going from 100 to 50, and I am stepping up the current. But in referring to this side, you are saying, oh, I'll basically pretend that the Z is on this side, but on this side, the voltage is up and the current is down. So if voltage goes up and current is coming down, what happens to your impedance? It's up. Now, voltage goes up by a factor of n. Current comes down by a factor of n. So impedance should go up by a factor of n squared. Do you get that? Because impedance is voltage divided by current. So if voltage is going up by a factor of 5 and current is coming down by a factor of 5, so your numerator has gone up by a factor of 5, your denominator has gone down by a factor of 5, so that gives you a factor of 25. Very clear mathematics. So therefore, we're going to multiply here by n squared. So it's n squared. And similar for the rest, because everything gets multiplied by n squared. All the impedances on the secondary side gets multiplied by n squared. So you'll have R2 prime becomes R2 times n squared, and x2 prime is x2 times n squared. Okay, so we know what to do to convert the transformer, the real transformer, having the real ratio being n1 to n2. We know how to replace that by a ratio of 1 to 1. And when you do this, all the impedances on the secondary side are changed by a factor of n squared. That's good. Of course, what also happens, and we have said this in this example, what also happens is that your primary side voltage becomes the same as your secondary side voltage, because this is 1-to-1. So if we call this E, which is quite legitimate to call this E, this one will also be E. The dot notation is important, but I think we won't worry about the dot notation for now. It's just that those two voltages, when you measure this voltage, not only the magnitude of this voltage is the same as the magnitude of that voltage, but they will also be in phase, because this is AC, so we have to talk about phase as well. So those two voltages, this transformer being 1-to-1 will mean that the voltages are not only equal in magnitude, but they will also be equal in phase. Some people might say, oh, they may be 180 out of phase. That's possible. It all depends which one you're using as your reference terminal. But we have defined it. If you want the exact representation, you put a dot there, meaning that both are pointing towards a dot, and therefore they are in phase. With the current, if I call this current, I can give it any name. I think I1 is fine. So well, I'll just call it I for now. So I'll call it I. So this current is I. What would this current be on this side? It has to be I, because that's 1-to-1. So this is E, this is E, this is I, this is I. All that we've done here hasn't changed anything from the point of view of the primary. Now comes the magic. And I say many people don't tell you that. And this is the magic. Have a look at this now. This circuit. I will redraw it. Oh, I'll put this on that side. Doesn't matter, obviously. Prime x2 prime z prime. Okay. So we go from here to there. And you may have seen this before, that so-called exact equivalent circuit of a transformer. Now, what allows me to go from here to there? What allows me to go from there to there is no equation or no theory. It's just obvious. It's so obvious you don't write anything down. Because look, this point here, relative to that, if I do everything relative to that, these two nodes and those two nodes, they are exactly at the same voltage. So I can actually join them without any problems. These two currents, they are the same. So I can pluck this out, take it out, and just join that to that one. It's exactly the same current. Another way of saying this is this one here. If I had a 1-to-1 transformer, which this is, and I put it in people call it a black box. I'm not sure why. Well, I know why, because you can't see what's inside, so they call it a black box. So if I had a black box, which I've drawn in red, but that's okay. So this is a black box. Inside it, so if I bring a black box to you with 4 terminals, 2 on this side, 2 on the other side of the black box, and I say to you, look, give me $50. I'm selling you a perfect transformer. And you say, oh, Tony, that's a good bargain, perfect transformer. And I tell you 1-to-1, it's a 1-to-1 perfect transformer, and give me $50. Now, and I said to you, look, this is true, it's 1-to-1. Indeed, if you put 50 volts there, AC, you can see, I'll prove to you there's 50 volts there, and I say to you, look, we'll inject so that it's 1 amp, so we put 1 ohm or whatever, 50 ohms on the other side, and that gives 1 amp, and you see 1 amp there, and you say, well, theory perfect, it's 1-to-1, 50 volts primary, 50 volts secondary, 1 amp, that fits every theory you've ever learned about the perfect transformer, and you say, okay, there's your $50. So what could be inside there, inside the black box? What are the possibilities? It could be 2 wires. Or it could be perfect transformer, 100 turns to 100 turns, or 200 turns to 200 turns. Or it could be 2 wires. So electrically, it's equivalent to 2 wires. So that's why I can pluck this out and put 2 wires. Okay? Would you give me $50? Oh, that's not good. Okay. So that's what many books will not tell you, why you're able to do this. And being able to do this obviously has simplified this for you. If you look at this and you say, I have to analyze this, in reality, how many circuits do you have there? How many electrical circuits? You have 2 electrical circuits there. 1 electrical circuit on the primary side and 1 electrical circuit on the secondary side. They are linked by a magnetic circuit here. So you have 2 electrical circuits and 1 magnetic circuit to analyze. By referring everything to the primary side, that is, refer those values to the primary side, in other words, convert the N1 to N2 transformer to a transformer of 1-to-1, and in that conversion, you haven't done any more approximations. In doing that, you're able to replace the perfect transformer by a pair of wires, which you have done, and therefore now you no longer have 2 electrical circuits coupled by a magnetic circuit. You now have, what do you have? What's this one? How many electric circuits there? 1. Just 1. So 1 electric circuit, no magnetic circuit to worry about. So that's the development of the transformer equivalent circuit. Have you got any questions so far? Okay. So this is not about plugging numbers in. It's finding out where do we get this. And it is important because I talk to a lot of people out there, and I talk to them and they do tests on their transformers. They got, you know what they call a test plan. So they take their test plan, jump in their ute, drive to the substation, get their test gear, which is sometimes a variac. They connect it to their transformer, wind it up, measure some current and voltages, do some calculation, and get a value. But how do these things they are doing, how does it relate to the theory? And that's what I'm trying to do. I'm trying to get you to understand the relationship between the theory, the physical device, and the test that you are likely to do if you are working in that industry. Anyway, let's keep going. So as we keep going, we further simplify, and I will say that we've gone now to here. So we've gone from here, we've gone to there, and then we've gone to there, and now we're going to there. So now we'll make an approximation. The approximation that is normally made is this one. And I rarely see people not doing this approximation. And I'll jump a step very easily there for you. Or maybe I'll put them like this because that relates to practical better. So put them separate, whereas these ones here, I'll add them. So x1 plus x2 prime, I'll add them, and I'll put that here. X naught and R naught. And if you did have some load, then that would be there as Z prime. So there is an approximation, and you can see. So we have approximation here. So you've made an approximation. You've taken this, which is in the middle, and you've shifted it to this side. That's an approximation. Now, under what circumstances would this approximation be okay? So it's okay to make this approximation for a power transformer. And what I would like you to understand is why is this approximation fine? You don't make big mistakes by making this approximation. In other words, we have taken that from here and we've put it there, like I've done there. Yeah, I'll give you a better approximation, even better than this, because that's what's assumed normally. So instead of taking it here and putting it there, which you can do, that's no problem, you can also take it there and put it here. That's actually a more useful approximation. So you do it here. So that's R naught and XM, I think it's normally called. XM. It should be XM. So why, first of all, under what circumstances is this approximation okay? And as I say, this circumstance happens all the time in practice. You can take that from the middle and put it on the end. It's much more convenient to put it on the end here. So why is that approximation fine? You don't make a lot of errors in going from the so-called exact, that's called an exact, so-called exact equivalent circuit of a transformer. I don't like it when they call it exact, but I'm prepared to live with it because everybody does. Why is that exact? Of course, and this is approximate. I'm not happy with the word exact because this is not really exact. It's exact only from the point of view of resistances and inductances, but there are capacitances that have been ignored there. So that's why I'm not happy with it. But as I say, people do call it exact equivalent circuit of transformer. This one is called approximate equivalent circuit of transformers. It is approximate because you've taken that and you've put it there. Now, why is it okay? Why is this approximation okay? Have a guess.
Because the impedance of that circuit is high compared to the other, so the current is going to be very small.
Which one is higher? Which one is higher and which one is not?
The impedance of the branch that you moved, which is there.
Yeah, that's right. So this here is a much higher impedance in practice compared to them. And if you go away and you can either prove it mathematically or you could go away and put some numbers in and you would see that this is quite okay. Analyzing this circuit is it's doable, of course. I can, if you give me some money, I can write a MATLAB program for you to analyze this circuit. I'll charge you the usual rate, consulting rate, which the university actually does get into the consulting business. And if you wish me to do that, I'll just tell our accountant here. And I think these days it's about $400 an hour. I don't get the money. The university, of course, gets it. and I'll write a MATLAB program for you to analyze this one, which is a little bit harder. This one is a lot easier to analyze, because once I give you the voltage, you will know what current goes there, because the voltage is defined. Whereas with this one here, if I give you the voltage, you can't tell me what current goes there until you have analyzed the whole circuit. So that's why it's easy. This one you can do in 2 MATLAB lines. That one you would have to write a bit more, right? So if you want me to do that one, I'll charge you still $400 an hour, but it will take me 10 minutes, and this one will take me half an hour. So there's an economy here in going from that one to this one. So, as you said quite correctly, that is okay to do because these impedances are much higher than that one. The no-load current goes through here, and no-load current of transformers would be typically only a few percent of the total current. So in practice, at full load, the current that goes there is a lot more than the current that comes here. Indeed, if you were to compare just that with this, in other words, if you short circuit this, then you virtually have no current here. So this could be thousands of times bigger in impedance compared to that. So that's why it's okay to put it on the end. It's a small number anyway. Okay, so that is approximate equivalent circuit, which is excellent, which is good. Now we're getting closer to question 1 of your assignment, and also closer to understanding what we mean when we talk about transformer impedance. Now, in doing that, I would probably like you to, in your mind, go back to this when I was trying to sell this to you for $50, and you said, oh, I'm not going to give you 50. None of you did. So all of you said, I can't give you $50 for just 2 pieces of wire in a box. Now, you can see that as you idealize this, that's what you get. See, this is the transformer here. We're calling this a transformer. It's a perfect transformer plus imperfections. So in here is a perfect transformer, 1-to-1, because we have converted everything to 1-to-1. So there it is. And as you look in this box and you say, make everything perfect, you will see you get just two wires. So if you make the transformer perfect, what happens to R0? Infinite. So no connection there. Similarly, the magnetizing current would be 0. So this is infinite. So this goes away. As you make the transformer perfect, what happens to R1 and R2?
0.
It becomes 0. And what happens to leakage? No leakage flux, therefore this is 0. So this becomes a piece of wire, and that becomes a piece of wire. So a perfect transformer, its equivalent circuit, is just 2 pieces of wire. And you can see how this happens here. So in doing this, you understand your equivalent circuit. You are not copying the book. You understand what you're doing. And I emphasize this so much because, as I say to you, I talk to people out there all the time. And it so happens these are the questions I get. They would say, oh, I'm going to do a test. I'm measuring this. What does it mean? And it always comes back to this first principles. So that's why I emphasize them. Okay, let's continue. So now, when you deal with those transformers, you do a couple of things. There are standard tests that you do on transformers. And what test do you do on transformers? Some of you at least have been here for a bit. So what test do we get you to do on transformers?
Open circuit test.
Yeah, you do open circuit tests, you do short circuit tests. There is another test that we do here on transformers. Back-to-back tests, which I love the back-to-back tests. They don't do it in practice very often, but it's a very clever test. If you want to know why it's clever, just let me know. I'll tell you. It's very clever. Anyway, short circuit test, open circuit test. Most people are aware of that. Open circuit test would allow you measure R0 and XM. In this course, we don't worry too much about that. But it's good to know that it's there. And if you did have to worry about it, you can just plug it back in. So in our business, we very rarely worry about it. So we further simplify. So for this course, we further simplify. So I'll unfortunately have to rub this off. So rub this off. And we'll further simplify. So we further simplify. So here is simplify. And when you do, you neglect the parallel branch. And when you do that, I'll just call this R. I'll call it RE. And this is R1 plus R2 prime. And this is X1 plus X2 prime. And so this is your transformer now. So this is your transformer. And many people call this summation, many people call it a transformer impedance. So you would have your excuse me, your load there. So that's a transformer. And as I say, they call this a transformer impedance. If I were to say to you, what is the transformer impedance of a transformer that you bought, how would you know? Nameplate. So that's the impedance that appears on the nameplate. So if you have a transformer at a substation, read the nameplate. That's what appears there. Not this one. Not this one. It is this one that appears on the nameplate. People also measure it, and as we just said, you can easily measure it by doing a short circuit test. Of course, if you put a short circuit here and you put a voltage here, you don't put a big voltage. Every year we blow about 10 fuses in our labs because people do short circuit tests and don't realize that if it's a 240 volt transformer, you can't put 240 volts there and do a short circuit test. And we get our staff upset when this happens and say it, so you better be careful. Did we blow some yesterday? No, we didn't.
I told them
Yes. Okay. So, so be careful. You do your short circuit test. You normally do a short circuit test at the rated current. So you would have a variac here. You turn it up until rated current flows. Then you measure the voltage, and the voltage divided by the rated current would give you that impedance. And that's what we call the transformer impedance. So the transformer impedance, it's mostly, in a good transformer, it will be mostly related to the leakage. So the leakage flux is what determines the transformer impedance. So if you want more transformer impedance, you have more leakage flux. And sometimes people say, oh, give us a bit more leakage flux so we have a bit more transformer impedance. Can anyone guess why sometimes we may want to have more transformer impedance? Yeah, that's, I'm happy you said that because I wouldn't have said that. So, yes, you may have to match impedances. Many times we connect transformers in parallel. Why would we connect big power transformers in parallel? We parallel them. redundancy. That means if one had a fault in it and was automatically disconnected from the system, the load is still supplied with the other one. So for redundancy. And when you're supplying an important city like Toowoomba, we don't want it to go blackout because one transformer had a fault in it. So to prevent the blackout for important people living in Toowoomba, like us, we would like some redundancy at the substation. So at the substation, we have two transformers connected in parallel, feeding the city of Toowoomba and, of course, other cities. And if one of those transformers was in trouble, then the other one would take up the load. The one that's in trouble would be automatically taken off the system and will be supplied then from the one transformer. That's one reason. Of course, there's another reason to have transformers in parallel. That would be if one couldn't supply the full load, then they could share the load. But normally, for continuity of supply, you would like to be able, especially if it's a big load like the city of Toowoomba, you would like to have redundancy there. So that's the other reason. So there are two reasons there for paralleling of the transformers. And when you parallel, if you want them to share equally or share according to their ratings, then you would adjust the impedances. Now, what's the other reason for maybe wanting to raise the impedance? When you buy a big transformer, like you would have spent millions of dollars, what would be the one thing you would like to do when you put that transformer in operation?
Make sure it's safe, runs safe.
Yeah, you would make sure it runs safe, etc. What's the word, the key word? The key word is the other course, which apparently you're not doing, protection. You would like to protect it. And what do you use to protect the transformer? The bus? What do you use to protect your house? Circuit breakers. So you have circuit breakers. With circuit breakers, the cost of circuit breaker will depend on what? The amount of fault current. You could use, at least for faults on, for faults that's happening on the secondary side, you could, your circuit breaker cost could be reduced by having more leakage in the transformer. That is your fault level. The fault level, at least for faults on the secondary side, the fault level on the secondary side can be reduced by having a transformer with a higher leakage. So because, as you can see, if you put whatever voltage here, if you had more leakage and therefore more impedance, this fault current on the secondary side is going to be less. So if you wanted to reduce your fault level, you could have more leakage. So these are reasons why you would have different impedances. And as I said to you in the last lecture, you can design your transformer so that it has more or less leakage. But you can never make the leakage zero, of course. There are situations in power electronics. How many of you doing power electronics? None of you, right? I did it last year. Okay. So in power electronics, sometimes you need one-to-one transformer with minimum leakage. There are two things you can do to do that. How do you get a transformer one-to-one with minimum leakage? How do you wind it? You use what's the so-called bifilar winding. So your primary and secondary go together. If it's one-to-one, you can do that quite easily. And when you do that, as you can see, if you've got two wires going together, the opportunity for leakage would be minimized. You understand that? Bifilar, so that's the term. And you also wind it on a special type of core. What is a special type of core? That has got minimum leakage. And you have to wind it toroidal. So you use a toroidal. So you use a toroidal core with your turns uniformly distributed around this core. You can do this at home on paper, I mean. So you draw that on paper and you try to draw the leakage flux. You can't do it. You can say, where's the leakage going? You find it can't go anywhere. The flux has to stay in the core. If you understand leakage, you would see why the toroidal core is superior to reduce leakage and why you have to have your winding uniform around the core and why the bifilar winding helps you reduce leakage to zero. So if you don't like leakage, go bifilar and go toroidal. Right? Okay. So we get to here. So that's you can measure that, as we say, using the short circuit test. By the way, I sort of kept that separate because in practice, you tend to measure that by measuring the winding resistance separately. So in your test plan, you would have separate measurements of those two because that can be done, and it's done with DC. And you may have a correction factor if you're worried about skin effect. And that one, you can get that one separate if you wanted by taking it away from the impedance. The impedance you get by doing the short circuit test. But most people don't get that separately. They just assume that it's approximately equal. If you wanted it, it's approximately equal to Z, because normally R is smaller, much smaller than X. Okay, so you would need this impedance in question 1 of your assignment. I give you a value for this, but I wanted you to know what the value means. And it's taken me 2 lectures or 3 to tell you what that value is. I want you to know what the value means. I don't want you just to say, oh, it's 0.1. What does the 0.1 mean? Thank you. I'll see you again.